Yeah, thank you everyone for coming in person or attending remote. Better speak here. So those remote can listen. Yeah. So Professor Jorge Gonzalez Cruz from the Atmospheric Science Research Center, and I have the honor to introduce our speaker for the Falconer lecture. That is a pillar of our lecture series for Atmospheric Science Research Center, honoring our colleague Falconer. So, Lloyd is our speaker today, and it's a great privilege to have you. Thank you for stopping by. Really appreciate it. And I have known Lloyd for some time, and he's just a tremendous colleague, scientist, infinite curiosity. So I admire that from him, and his will to support the younger generation. At the AMS, all machines were asking, who is this? You're asking a lot of good questions. And so we appreciate that very much. And we learn from you and respect you tremendously. So formally, currently, Lloyd is a research scientist here at the Atmospheric Science Research Center. It's a great privilege to have you in our group. And his current research interests include the impacts of our warming planet on water and energy, and the feedbacks on infrastructures, design, and policy, both on sustainability and the climate system. In his previous role, that's where we got to know each other. He helped lead IBM research and development in environmental sciences. That included the practical and proactive use of advanced modeling for decision-making in short term, highly localized weather-sensitive business operations, such as electrical grid resiliency, integration of renewable energy resources, modeling of water lake watersheds for water quality, and to that is I think it's still going on the very unique test bed in Lake George.
We're about that.
There you go. So great. I think it's just a landmark science effort that we're still learning from it. It's just phenomenal. And he was the architect for that project. He gives a lot of time to society, currently the board of directors, and is the previous chair of the Water Rising Institute and a member of the AMS Water Resources Committee. He was also a member of the Climate Change Subcommittee of EPA's Board of Scientific Counselors and a sector advisor to New York State Climate Impact Assessment Board. It's a great privilege to have you here. Thank you for stopping by. We look forward to your talk.
Thank you.
Good.
Good evening, everyone. Before I get started, I want to do a shout out to my colleagues from RPI and from ASRT listed there. And three of my colleagues at RPI, Guillaume, I didn't see you walk in, but say Guillaume Majer, Chris Moriarty, and my colleague, and we'll be referencing some of their work. Just I want to reiterate my privilege that I feel in being able to give this a lecture in the Ray Falconer series. I never met him, but I know of his work, as being, as I understand, the first employee at ASRC. But he had a tremendous interest in environmental topics. And of course, the influence on the Earth's environment, from, of course, with no bias on my part or perhaps Jorge's part or others, everything starts with the weather. And so I think he would have an appreciation for some of what we'll be discussing today. So I want to give some background, to some of these questions about how we could improve freshwater, our understanding of freshwater resources in New York State. Some of the challenges. I want to talk a little bit about some of the work that our team and I have done over the years, and some of the new work that's ongoing. So, just as a reference, the challenges for people who have access to clean water are enormous. And when we think about a significant fraction of the world's population, they don't have access to regular water, and that also includes a sizable number of people within the U.S. Some of that directly, others are more indirectly because of the water infrastructure that they use is unreliable and has many issues in operating consistently. And an important aspect also, is the significant fraction of the people that have this lack of water, are essentially underserved, and including in the U.S. So this is a map from some work that was published last year by Meehan et al. And it's showing the distribution of households without running water across the U.S. And you can see large concentrations of this in urban areas. There are many reasons for the stressors in each of the urban areas, but it's worth noting, where these concentrations are. They're in populations that are at lower socioeconomic conditions, or have other systemic infrastructure problems, which leads to this lack of access. But it's these kinds of issues, we want to keep in mind as we look at the rationale for wanting to do better in our understanding of resources. So as I mentioned, that poor, especially isolated, communities are at the at the greatest risk. But now there are additional.
Can you hide this toolbar?
Yeah, I was.
Just move the cursor away.
Yeah, move the cursor away. There it goes. Yeah. Okay. Yeah, I couldn't tell if what I was seeing reflects exactly what's on the screen, as opposed to the what Zoom is doing. So I'll keep that in mind. Thank you. So these risks or these conditions are being essentially exacerbated by a number of stressors. So this ranges from the aging infrastructure that I had mentioned, but there's also increased demand and impacts from a warming planet. There's feedbacks between these. There's also concern about relative security of water systems. But we're also seeing additional changes and leading to impacts at a local scale. So it's a growing problem with sort of local impacts in the sense of, examine, water intensive manufacturing, expansion of data centers requiring water for cooling and or energy generation, changes in agricultural practice, and then look at the effects of runoff from storms in an increased climate. So again, these are all feedback mechanisms. And one of the areas that I'll talk about will be, what that runoff can lead to additional nutrient loading and potential formation of harmful algal blooms. And so we'll have this is both a local and a global problem, just on a more local scale. So here's just two examples of harmful algal blooms at two of the Finger Lakes from a couple of years ago. So let me give at least kind of a brief introduction about harmful algal blooms, in case, I know some of the audience are very familiar, but perhaps most of you aren't. So one aspect of this is that, phytoplankton is ubiquitous in ecosystems around the world, but some of the species can lead to harmful impacts on people, wildlife, and they can sort of change rapidly, over certain timescales and create these blooms in water. This is both This can occur both in a marine and a freshwater environment, although we'll be focusing more on freshwater here. And these are increasing over time. At least that's been the, what's sort of been causally observed. So you can sort of see this in the map on the right, which is focused more on the marine environment, which you can see from half a century ago or earlier that it was a very rare occurrence, but more recently it's occurring quite often. And again, there's a number of stressors that could be leading to this, and it's some of the same ones that I mentioned before: changes in agricultural practice or other water-intensive activities, a warming planet, etc. And some of these issues were front and center in the discussion in the New York State climate assessment, looking at the water impacts of the impacts of climate change on water resources within New York State. So again, with a bias towards weather, there is kind of some simple considerations with regard to how tabs could form. So kind of think about some of the recipes that might be needed kind of on an average scale. It has to be warm enough, there has to be enough nutrients, and the water has to be thermally stable, so on average. So there might be mixing that could occur from material that's at the bottom of the freshwater body, and through some mechanism that may come closer to the surface, have access to nutrients, have access to sunlight, and then lead to formation of blooms. There may be mixing going on in the water that could lead to further recycling from the lower levels, and wind across the surface of a freshwater body could influence this type of mixing. So I'm going to get back to some of these ideas, but keep these in mind for some of the points I'm going to be introducing a little bit later. So just to give you a little bit of information about what's the impact of these blooms from a, let's say, a socioeconomic perspective. It's been difficult to quantify sort of accurately because of the lack of information about, let's say if it's public health, somebody's coming in with respiratory distress. Is it from aerosolized cyanobacteria from blooms, from some other source? So being able to separate the cause, it adds to some of the difficulty in putting more precise information about the impacts. But from U.S. Agencies and academic organizations like Woods Hole, they estimate that on the average it's going to be a $50 million impact, with a significant fraction related to public health. But there's impact on fisheries, on recreation, and there are costs associated with that. If there's a large HAB event, then these costs could be in the order of $10 million. And so we see examples of this with the red tide in the Gulf of Mexico off the coast of Florida. We see this in Lake Erie, and also in the San Francisco Bay. So then the question is, well, do we see these kinds of issues in New York City? Well, there's the answer is generally yes. There's been wide-scale reporting of for many years by New York State agencies looking at HABs. So here we see an example of a sort of aggregate number of reports from 2012, and that were reported by the New York State Department of Environmental Conservation. These are locations that are confirmed by their staff, either by photographs or laboratory analysis of water samples. And just to put some of that in perspective, if you look at these reports in 2025 as a relative to the number of reports for the surface area of the lake. We see some familiar lakes of interest, at least to some of us, or having a relatively large number of reports for each square kilometer of area. And here's another way that the New York State has been reporting these reporting HABs. And so here you're seeing from 2012 to 2025, if you look at the trend, you could say, well, it sure looks like it's increasing, but this is aggregated over the whole state. But one of the things we can't sort of disentangle from these statistics is, well, this agency and other agencies has been doing a lot of public outreach, teaching about HABs, and we also have seen this in federal agencies as well. So are people now, reporting and then they get verified because there's somebody there looking? So that becomes a problem. We don't then know how reliable the historical data are, or that there's duplications in the more recent data. So this creates a challenge to understand trends. But this, also gets to some of the issues that I'd like to talk about today. So we can argue that there are clear goals from the state agencies. They're focusing on monitoring, assessing how to mitigate, do planning, doing outreach and education about HABs. But the methodology is primarily focused on looking at the surface or near surface. So this is either through water samples that are taken back to laboratory analysis, it's photographs. There might be online instrumentation, but it's at very low spatial or temporal frequency. And so there's a lot of data, but sort of insufficient. We'd also argue that the focus is primarily on observation from a monitoring perspective. There are scattered efforts in modeling through a variety of techniques, but they're limited in the context of these efforts, and they're not integrated, and certainly not operational. Not integrated with observations, they're not operational. There's also some use of remote sensing. So this is imagery from orbital platforms, but not adequately leveraged. It's using mostly older systems. So we have an issue where the typical data are incomplete. They have insufficient fidelity for many of the kinds of applications that we might be concerned about. And this is all reflected on current approaches by the state agencies, both in terms of their ongoing roadmap and their multi-year research plan. So, what are some of the alternatives? But before we get to that, I have to take a little bit of a diversion about remote sensing. So the idea of using optical imagery, from multispectral sensors on polar orbiters, has been well established for looking at these kinds of problems. And we have nearly global coverage. Here we see sort of a nice bad example. It's showing algal blooms in 2011 in the Western Lake Erie. And the blooms extended over 16 kilometers from the shores and into the Central Basin. And you can kind of see that through these observations. So these kinds of methods are very good at looking at large persistent blooms. But if you're now looking at blooms that are small or transient, these techniques have their limitations. But this is consistent with remote sensing in general. There's always some kind of trade-off. And this is based on the spacecraft orbit geometry, the kinds of imaging and of course cost. So the good news is there's very large volumes of openly available data to anybody for any purpose from the US and EU governments. But one of the issues is that this is reliance on essentially surface observations. It's what you can see reflected off of the surface or near surface. And this is really an approach that goes back almost half a century with ocean color on NASA spacecrafts. And just as an aside, I actually worked on some of those data when I was at NASA a long time ago. But the real issue here is that the bloom depth is not observable reliably from orbit, especially with optical sensors. One could argue that we need cloud-free viewing, so what about radar? Well, radar systems could be used, but they've not been shown to be reliable yet for this kind of problem. So then there's these trade-offs. One can get high spatial resolution, the order of tens of meters, and you'd have revisits every few days. But you have low spectral resolution. So that means that any assumptions about cyanobacteria are based on proxies derived from infrared reflectance. And so they're going to be unreliable under certain circumstances. If the water's too clear, you may get false positives by what might be sitting on the bottom, or they also be confused if, let's say the clouds are thin, but enough of having enough opacity in the infrared that you can get another false positive as well. Of course, if the clouds are thicker, you're not going to see anything. So there are other sensors that are low spatial resolution with daily observations, and with enough spectral resolution that you can get much more reliable detection, and even with the potential of determining if a bloom is harmful or not. And there are some alternatives out there, but at a higher cost. There's constellations of spacecraft in low Earth orbit that are operated commercially, and they could have very high resolution spatially, and then being updated like daily. Another high cost alternative for a very localized scale is putting a multispectral camera on a drone, but that's also not cheap either. There is some good news, is that while a lot of these methods are based on well-established technology, there are newer systems that have been launched over the last couple of years. One by NASA, which will focus on very high spectral resolution to be able to do species identification. Another is a joint mission by NASA and the Indian Space Agency using dual radars in orbit. The revisit time would be like of the order of 10 to 12 days, but one could see through the cloud deck and operate at tens of meters resolution. So these are some interesting promises with new types of instrumentation. So let's talk about let's get back to the issues that I had introduced, and I apologize for the diversion, but as somebody that's worked in remote sensing, it's I can't resist the diversion. So one of the things that we want to think about is that the monitoring of the water environment and its modeling are really sort of two sides of the same coin. So if we go back to sampling theory, one could cast both of those as methods to sample a volumetric environment dynamically. One is physical and the other is virtual. In our case, we think about the virtual as, being a computational simulation, using numerical methods, but it doesn't have to be limited to that. It would still be a model. But what we would argue is that they both need to be at the appropriate scale for whatever phenomenon that you're looking at. So this is where we bring up the problem, let's say, related to HADS, the typical approaches are not introducing the sampling at a scale that fits the problem, but also a scale that's, one also has to have that scale that it's also sort of computationally tractable as well. So there are compromises to consider. But in combination, we can think about how observations and models work together. So when we think about just the observations, now that includes both, measuring as well as, let's say, observing remotely from orbit. You can use that for real-time monitoring. You can do historical data analysis. You can train data-driven models. These days that would be viewed as being, AI and machine learning methods. But this is also not necessarily a new idea, because one could use statistical methods, and that still has to be trained in a data-driven sense. And when we think about models, well, the usual example is a predictive model. So you see a weather forecast on your phone. That's being derived primarily from a simulation, of forthcoming weather. But now we can combine them. So if we want to use observations associated with the models, we can use a process called data assimilation, which reduces the errors in the initialization of the model and improves its fidelity. We can also use those observations to determine, well, how good is this model, and how can we tune it. And similarly, you can use the simulations to associate with observations. You could do experiments in the design of an observation network using simulations. Or if you have both of them coupled together, you could steer or change modes of operation based on what a predictive model might say. So we've tried to put some of these ideas in practice, over the last decade. So this was what we called the Jefferson Project, and this was initially work that was done at Lake George. My colleagues and I at IBM Research did this working with RPI and with what is now a nonprofit, the Lake George Association, and with the idea based on a longitudinal study that was done over multiple decades that looked at stressors in the watershed. Can we understand how this ecosystem is changing from any of the stressors that I had mentioned? It has one advantage as a laboratory. It's very clean. So it doesn't have a lot of the stressors that we see in other places. Not a lot of agriculture, no significant industry, not huge changes in land use over multi-decades. So that allows one to look at the watershed in a more consistent fashion over the long term. And there's a number of characteristics of the lake. I won't go into detail about that led to this being an ideal choice for this kind of work. But what we developed was this idea of coupling the modeling and the observation. So this was sort of interplay that I had outlined conceptually. So here's putting these kinds of ideas, in practice with a number of different models that operated in conjunction with each other and the observations. And so I can show you a little bit more detail. So here we see a map on the left of the Lake George watershed with a number of markers showing various observation sites. So this includes, I have to start with weather stations, includes weather stations. So, but also includes vertical profilers, so devices that observe not just at the surface, but underneath the surface. I'll show you some pictures in a moment, and instruments in the tributaries that feed into the lake. Large amount of data has been acquired through the many years of this effort, and some of the statistics are shown there. But it's a sort of an unprecedented data volume for a watershed effectively this time. So if any of you have visited the Lake George area, you might have seen some of this handiwork and some of this work that Mike and Vincent in the audience. They did the actual deployments of some of these devices. So platform, on the lake surface, it takes measurements through the column down, and then also using acoustic techniques to look at conditions as well. Standard weather measurements from that platform, as well as fixed sites, and then stations that are measuring the water quality and the flow in major tributaries. This work also included developing a platform to be able to collect and disseminate the data. So again, handiwork by colleagues in the audience to develop the underlying hardware and software and deploying it so it can all operate automatically, reliably, and to enable the data to be used for the kinds of purposes that I outlined earlier. That observations network is still in operation, now taken over by RPI. Actually, if you go to the URL at the lower left, you can take a look at current observations from these sites. So on the modeling side, what we did is, well, we started with weather, okay, but the idea was trying to match the scales at which we're concerned about the impacts in water. So that's difficult to do, from the weather perspective. So if we wanted to do that with typical weather models, we would have very few data points of the watershed, so insufficient information. So we essentially had to introduce a weather model that would operate at 2 orders of magnitude more detail than the kinds of weather models that you would see from government or private entities. And then we use that to drive a model of the land surface, focusing on hydrological processes. And again, at a very fine scale, 41 meters for the entire watershed. And then driving a lake circulation model, which captures the 3-dimensional hydrodynamics of the lake. And that's at a variable resolution, tens of meters. So again, sort of unprecedented scale, but this idea of trying to get to a scale that sort of matches the phenomenon of interest. And I think I'm, just in the interest of time, I think I'm going to skip through a couple of these to get to some more interesting developments. But just to also put this in a geographic scale. So one of the ideas is kind of like creating a 3-dimensional magnifying lens over the lake. So we start with the broader scale with weather on the left, using a technique that's telescoping nests, so finer and finer details, so down to a third of a kilometer. And then that's used to drive the hydrology at 41 meters, and then both of those are used to drive the hydrodynamics. And this is sort of a one-way coupling of each of these. Get this just as a little bit of a teaser. With the 3-dimensional data, we can do fun things or useful things by looking at all of the data. So this is just showing a thunderstorm over the watershed. We can visualize individual thunderstorm cells from the model, along with clouds and precipitation and winds. If we're interested in winds, we can also apply some of the same methods. And now we're looking at surface winds, but also upper air winds. So that kind of white surface that you see kind of rolling back and forth, that's a surface at 40 miles an hour. So above that, the winds are higher. Below that, the winds are slower. And it was during a frontal passage, and you kind of see that it's sort of a wave and the winds well above the ground. And the model's capable of simulating. Skip that, just briefly talk about the hydrology again. This is meant to operate at a very high resolution to get closer to the scale of being able to simulate individual streams and stream segments within the watershed. And this is just an element here that I mentioned before, is when you have models and observations, you want to see how well the model performs. So this is showing over a year period. For example, the red line is observations, the green line is the model. It's not perfect, but to be able to capture this sort of detail, at an individual, sensor station is a difficult problem, and we come pretty close to that. The simulation of the lake hydrodynamics, also all these are three-dimensional models, and the idea here is to being able to capture a lot of the structure, how it's influenced by the bathymetry, the topography of the surface, and how it's forced by the weather at the surface. So I'm just sensitive to the time. I'm going to I'm going to skip forward a little bit. Okay. So and one of the things that it's a big deal is how this project is moving forward. So the timing of the talk is this talk today is good because we had a formal announcement just last week where ASRC is now formally part of this project, and working with RPI, the Lake George Association. So as part of that, the coupled modeling will be being brought back online here at ASRC, and the New York State Mesonet will be extended with 2 sites in the watershed. But an initial observing system is already in place, and you can see on the map there's 2 vertical profilers. Where the red locations, there's sediment tributary stations, and then the 2 weather stations are shown roughly where they'll be placed. The data are also openly available from the existing sites as well, working with the Chautauqua institution. We have a similar setup for a couple of models, following the same methodology that we used. So now I'm going to come to the fun part. Okay, so this is work by Mike Kelly, sitting in the middle back here, and it's showing simulated temperatures from the model from a period of mid-August to mid-October of 2023. So the bottom temperatures are, if you can see my cursor, bottom temperatures are to the right. The surface temperatures and the forcing wind from the weather model are shown on the left. So the bottom portion of the lake during this period is dense and cool, and compared to what's close to the surface. But as we move through this period, one of the things that you want to see is how the temperatures are changing on both panels, and as a function of time, but also in terms of location, the North Basin versus the South Basin, for example. And if you look closely, you'll see a turnover where these temperatures change and become more uniform between the top and the bottom. And this is sometimes called, for lakes like this, a fall turnover, but this is occurring in the end of August, not in the fall. So one of the issues is that there's an assumption that the turnover occurs only in the fall because it's based on these notions of just surface observations. You don't have detailed observations, and you don't have 3-dimensional models of the lake. And the model also allows this more realistic representation of this kind of transition in the lake. So how do we know this for sure? Well, this is why you have both models and observations. And I can make a model and I can issue a prediction. And how do I know it's right? Well, you need to have observations at the right scale to actually determine that. So there's some complexity in this. So the key to look at is there's part of a map in the lower left, which is showing the location of the measurement. So that's the dark colored dot, and the red dot is where the model data are being shown. Because of the importance of wind, you see a wind vector at the upper left. So the key is looking over on the right. You're seeing a plot of temperature as a function of depth. And the blue line is derived from the model, and the red line is the observations. Now, the correspondence is not perfect, but it's pretty close. Okay, and why this is important? Because if you can validate at this scale, then this gives you some confidence that the model is actually doing things that make sense, and then could be used sort of reliably in elsewhere in the lake. And this is important with regard to HABs, because it really has to do with the mechanisms associated with the HABs formation. So if this kind of process is occurring at a different time of the year, earlier than expected, then that means the mechanisms associated with it are not based on the assumptions that, let's say, low oxygen is causing the nutrients to come up to the surface, but rather we're seeing a mechanical phenomenon, driven by the lake circulation, influenced by the weather, by the wind, and leading to nutrients being sort of moved up a column and then becoming HABs. So the last example I'm going to show is from Lloyd, who's sitting on the other side of the room from RPI. And he's also looking at, in this case, the top 2.5 meters of the lake, and looking also at the model versus observations. So we're seeing observations from two vertical profiles. So that's the plot on the top and the bottom. So the top is for the vertical profile to the north basin, and then the bottom one is for the south. And the plot reflects the potential for cyanobacteria. The plots in the middle are at 3 locations, 1, 2, and 3, 1, 2, and 3, and showing plots as a function of time, corresponding at the same time as the observations, for the volume of water. And so that we can see water being transferred from the south to the north in the green rectangle. And then if you look at the other sections, we don't see any sustained volume transfer. So this is important to understand the movement of not only water, but potentially nutrients from one basin to the other, that it might have an effect on HABs. It's another way to look at that. This is going back to the remote sensing. Now this is what you see for each of the pixels, which are its course at the scale of the lake, 300 meters. But you see and I can redo that. You can see as the lighter colors are indicative of increase in cyanobacteria. This again is a derived index. It's not being measured directly from orbit, but it's a proxy for that. And that's consistent with the observations, as Gio points out, from the vertical profile. So again, even if you're using different modalities of observation, being able to have confidence that what you're measuring in the water, what you're seeing from orbit, are consistent with each other. We see many examples with ground truths not being consistent with what's seen from orbit and in other domains. So it's very important to, if you're bringing complex observations and models together, that you're able to sort of cross-validate again, it gives you confidence that the data that you're getting is suitable at the scale for making decisions. So, in conclusion, I'd like to think that this story has indicated that coupling models and observations has value when it's done at the appropriate scales, like for the watershed model. And certainly, we see this as being relevant in New York State and ideally beyond. So the team is, continuing this work, and part of it is extending the work to the Stockholm watershed. But as part of that, we hope to expand the observing system, and then reconstituting the models here at ASRC. We intend to enhance and further their fidelity, in conjunction, as part of this ongoing collaboration between University of Albany and RPI. And with that, hopefully we have some time for questions. So thank you.